In this lesson, we're going to cover Riemann sums. One of the most important unifying problems in calculus is the area problem. So here we have a curve, and what we're doing is we're looking at the area under the curve from A to B that's bounded by the curve and the x-axis. So for this diagram, we're calling that region S. It says right here, consider the area under the curve of F bounded by the x-axis and the lines x equals A and x equals B. We can find an approximation of the area of the region S, and to do so, we're going to divide the interval from A to B into subintervals where A is equal to x naught, B is equal to x sub n, and we're going to use what we call a Riemann sum, or a sum of the areas of rectangles to approximate the area of the region S. Our formal definition for a Riemann sum of a function f over an interval from A to B is going to be this summation notation where you start with I equals 1 to n. This says f of x sub I times change in x, where change in x, here's your formula, it's going to be b minus a divided by n. So again, a Riemann sum, so we have our summation notation, is a sum of areas of rectangles. And you can see right here, this is representing the change in x, or the width of the rectangle, and we're timesing that by the height of each rectangle. And then we add up the areas of those rectangles, and that total is going to be the approximate area under the curve from A to B. Our example says, estimate the area of the region S bounded by the graph of y equals x squared, the x-axis, and the lines from 0 to 1. To do so, we're going to divide the region S into n rectangles of equal width. So here's our region S. You can see it's the area under the curve of x squared, bounded by the x-axis, and then we're going from 0 to 1. So we're going to approximate this area, first, part A, by using right endpoints and 4 rectangles. Because it's right endpoints and 4 rectangles, our notation we're going to use is capital R sub 4. Before we calculate this, I wanted to point out again, change in x is b minus a over n. So if we needed to find change in x for this problem, we're going from 0 to 1, so b is 1 and a is 0. And because it says 4 rectangles, that's our n value. So we plug 4 for n, and we end up getting 1/4 is going to be our change in x. So again, 1/4 is the width of every rectangle. Next, this says right endpoints. So if you go from 0 to 1/4, the right endpoint would be on the right side, and you go up to the curve and you put a dot. So now you have this base and this height, and that creates your rectangle, and then you can multiply 1/4 times this height, and that will give you the area of that rectangle. For this next interval, if we go on the right at 1/2, you go up to the curve, put a dot, and that creates the height of the second rectangle, and then the width is still this 1/4. And again, the area of this rectangle is going to be 1/4 times this height. And you do that for the next 2 rectangles. To calculate the area for all of these rectangles, you could go 1/4 times the height at 1/4. And then for the next rectangle, it'd be 1/4 times the height, which is f of 1/2. And you'll notice because these rectangles are of equal width, each expression has a 1/4 in it, so we can factor the 1/4 to the front. So to find R sub 4, we factor the 1/4 to the front, and then it's just the right endpoint. So it's f of 1/4, f of 1/2, f of 3/4, and f of 1. And so that's written here. And then finally, I'm going to take this entire expression and plug it straight into a calculator. And we end up getting 0.469. And because this graph is increasing at an increasing rate, and we're using right endpoints, this approximation is an overestimate. For this next example, we're going to use the same curve, and we're still using 4 rectangles, but this time we're going to use left endpoints. So our notation is going to be L sub 4. Since the change in x, or the width of every rectangle, is still 1/4, I'm going to factor that out to the front. Next, because we're using left endpoints, we have our first interval from 0 to 1/4, and if you go to the left endpoint from 0 to 1/4, that's going to be right here, and then you put the point on the curve. So for this first rectangle, there's no height. We're going to do the same thing for this interval from 1/4 to 1/2 on the left. We go up to the curve and put a dot on the curve. So that creates the height for the rectangle, and then your width is still 1/4. For our next rectangle from 1/2 to 3/4, we go on the left and go up to the curve and put a dot. So that gives us our height. And then finally for our last rectangle, we go up to the curve and put a dot, and there's our height. So again, from here to here, you would say f of 0 would be the height. The next rectangle, because it's on the left, you go up to the curve. So to describe that, it's f of 1/4. For this next rectangle, again, you go on the left, and at 1/2, you go up to the curve. So to describe this height, we say f of 1/2. And finally, our last rectangle is going to be f of 3/4. And again, to find f of 0, f of 1/4, and so on. you're plugging these values 0, 1/4, 1/2, 3/4 all into the function y equals x squared. So for our approximation, we get 0.219, and because this graph is increasing at an increasing rate, but we're using left endpoints, this approximation is an underestimate. For part C, we're going to use midpoints for rectangles, so our notation is m sub 4. Since the number of rectangles hasn't changed, our change in x is still going to be 1/4. So again, the width of each rectangle is still going to be 1/4. To use a midpoint Riemann sum, what we do is we still go from 0 to 1/4, but instead of going on the left endpoint or the right endpoint, we use the midpoint. So we go up to the curve, put a dot, and that's the height of the rectangle. Okay, let's draw the next one. We're going from 1/4 to 1/2. So you go right in the middle, you go up to the curve, put a dot, and that's the height of the rectangle, and the base of the rectangle is still from 1/4 to 1/2. To draw our next rectangle, again, we're going from 1/2 to 3/4. We go in the middle, and that's the height of the rectangle. So you draw a rectangle whose height is right here, and the width is still from 1/2 to 3/4. Again, since each rectangle has the same width of 1/4, we're going to factor that out to the front. And remember right here, this midpoint between 0 and 1/4, that was 1/8. So I'm going to count this out. If this is 1/8, this is 2/8, this is 3/8. And if we keep going, this is 4/8, this is 5/8, this is 6/8, and finally 7/8. So when we write the heights of the rectangle, they're occurring at the midpoints. So it's going to be f of 1/8. Next, it's going to be f of 3/8, f of 5/8, and finally f of 7/8. So again, to find these y values, we're going to plug 1/8, 3/8, 5/8, and 7/8 into the original function y equals x squared. And for our approximation, we end up getting 0.328, and this is going to be a better estimate than taking a left endpoint or a right endpoint. This example says, estimate the area under the graph of f of x, which equals negative x squared plus 5, from x equals -2 to x equals 1, and then we're going to use, for part A, left endpoints and 3 rectangles. So this is A and this is B. To find change in x, we go b minus a all divided by n. Again, n is the number of rectangles. So for our change in x, we end up getting 1. So for part A, we're using left endpoints. So right here, we're going from -2 to -1. To draw our rectangle, we go on the left endpoint, we go up to the curve and put a dot. So the width is 1, and you're on the left, you go up, put a dot, and that creates your rectangle. We're going to do the same thing from -1 to 0. This is your interval, you go on the left, and you go up to the curve, put a dot, and that's the height of the rectangle. One more time, from 0 to 1, we go on the left. So at 0, we go up to the curve, put a dot, that's the height of the rectangle. So there's our 3 rectangles. Remember, each rectangle has a width of 1, so just to stay consistent so we get in the habit, I'm going to factor that width to the front, and then to write the height of each rectangle, it's going to be f of -2 plus f of -1 plus f of 0. Because we're using left endpoints and we're going from -2 all the way to 1, you don't end up using f of 1. All right, and this problem's nice because you can see the heights right here on the graph. So f of -2 is 1. F of -1 is 4, and f of 0 is 5. And we end up getting an approximation of 10. And then also you can see that because you have this big gap here and here not included in the area, and then you have this little excess right here, because again we're trying to approximate the area under the curve from -2 to 1, we would say that this is an underestimate. Okay, for part B, we're using right endpoints, 3 rectangles. For our next interval, we're going from -1 to 0. So you go on the right, go up to the curve, put a dot, that's the height, and there's our rectangle. And again, from 0 to 1, you go on the right, go up to the curve, put a dot, and that's the height of the rectangle. Okay, so this is going to be r sub 3. Our width is 1, so we factor that to the front because they all have equal width. And this time, because we're using right endpoints, we're going f of -1, f of 0, and f of 1. So f of -1 is 4, f of 0 is 5, and f of 1 is 4. And we end up getting 13. And again, we're going from -2 to 1, so it's the area under the curve. You can see that it's missing this much, but then we have added that much, and then you have all of this excess. So this would be an overestimate. All right, there you go. For this example, we're using midpoints and 3 rectangles. For our first rectangle, we're going to go from -2 to -1, and our midpoint occurs right here at -1.5. We go up to the curve, put a dot, that's our height, and our width is from -2 to -1. Our next rectangle, the midpoint is at -0.5, so we go up to the curve, put a dot, that's the height, and our last rectangle, we go to 0.5, or 1/2, we go up to the curve, and there's our height. All right, so we have m sub 3. Each rectangle has a width of 1, and the height for our first rectangle occurs at -1.5, or -3/2. The height of our next rectangle occurs at -1/2, and the height of our last rectangle occurs at +1/2. And for reference, I wrote the equation of our curve. It's y equals -x² plus 5. We're going to need to plug in these x values in order to find the corresponding y values. So I took -3/2, -1/2, and +1/2, and plugged them all into this function right here, and then wrote them out. And at this point, we're going to simplify. So I squared this, made it negative, squared this, made it negative, and then squared this, and then also made it negative. And then I added 5, 5, and 5 to get 15. And you end up getting 49/4, or 12.250. For this example, we're going to do left endpoints and 6 rectangles. To find change in x, we're going to go b minus a over n, where n is the number of rectangles. So you end up getting 3/6, or 1/2, and that's going to be the width of every rectangle. So I filled in -3/2 and -1/2 and +1/2. So our first interval is going to be from -2 to -3/2. So our first rectangle goes from here to here. We go on the left endpoint, go up to the curve, put a dot, and that's our height. And then I'm going to keep using left endpoints and draw the rest of our rectangles. All right, so I have them drawn in. Okay, so for notation, we have L sub 6. Each rectangle has a width of 1/2, so we pull that to the front. And then I'm going to fill in our heights. We're going from -2 to +1. We're using left endpoints, so we end up using -2, -3/2, -1, and so on. But what we don't use is we don't use the 1. So when we're plugging in these x values, you'll notice we don't have f of 1. And again, that's because we're using left endpoints. At this point, we're going to take -2, we plug it into this function, then we take -3/2, we plug it into this function, and so on. And you end up getting 89/8, or 11.125. This example says speedometer readings for a motorcycle at 12-second intervals are given in this table. Find the upper estimate for the total distance traveled during this time period. So what I did is I took these data values and I labeled our x and y axis so that going across the bottom is time in seconds, and it goes 12, 24, 36, and so on. And then I went up the y-axis in increments of 5, and I took these values and plot them, a really rough sketch just to get an idea of what the curve is doing for velocity. This problem specifically wants the upper estimate. So I just want to look at this, and we're either going to use left endpoints or we would use right endpoints. So if we did right endpoints, it looks like it's going to be an underestimate because the graph is curving down. So right endpoints would be below the curve. So again, because we want upper, I think we're going to go with left endpoints. So depending on the way your curve is going, that would tell you for upper versus lower estimate to use a left or a right endpoint. So from 0 to 12, to draw your left endpoint, you go up to the curve on the left, and then you draw your rectangle. So from 12 to 24, we go from 12 up to the curve, put a dot, and there's the height of our rectangle. And you continue doing that using left endpoints. Since each rectangle has a width of 12, I'm going to factor out 12 to the front. And then right here I put v of 0, v of 12, v of 24, 36, and 48. Again, because we're using left endpoints, we don't include v of 60. So from the table, we get that v of 0 is 30, v of 12 is 28, v of 24 is 25, v of 36 is 22, and v of 48 is 24. And then I'm going to plug this right into a calculator. So our upper estimate for the total distance traveled during the time period is 1,548 feet. This example says a car's velocity in meters per second at various times t from 0 to 30 is given in the table. Use a midpoint Riemann sum and estimate the total distance traveled by the car over the interval from 0 to 30. So for our table, we have the time in seconds going across the top. Then we have velocity in meters per second going here. Since the problem says that we're using a midpoint Riemann sum, We want to use the values that are presented in this table. So this is going to work perfectly for 3 intervals, again from 0 to 10, 10 to 20 seconds, and then 20 to 30 seconds, because our midpoints occur right in between at 5, 15, and 25 seconds. So we're going to set up a midpoint Riemann sum with 3 intervals. The first rectangle goes from 0 to 10, so the width is going to be 10. The next rectangle goes from 10 to 20, so the width will also be 10. And then the last one goes from 20 to 30, so that width will also be 10. So if you wanted, you could factor out the width of 10, again because each interval has the same width. So if we factor that to the front, again the midpoint occurs at 5, 15, and 25. We're going to get these values from the table, so v of 5 is 2, v of 15 is 9, and the velocity at 25 seconds is 20. And then when we add these up, we get 31. And finally, the total distance traveled by the car over the interval from 0 to 30 seconds is 310 meters. Next, we have a note. It says, in addition to using a sum of areas of rectangles to approximate the area under a curve, we can also use trapezoids. For a given region, the sum of the areas of trapezoids is called a trapezoidal sum, and then we use the notation T sub n, and then here we have the summation formula for our trapezoidal sum. For a quick reference, the area of a trapezoid is 1/2 the height times the quantity base 1 plus base 2. So this is essentially what's happening here. We have 1/2, and then this is the height of the trapezoid, but we are calling it change in x. And then we have base 1 plus base 2. And then the sigma is indicating that we're going to add up all of the areas of the trapezoids. Change in x is still b minus a over n. In this diagram, you'll notice the heights of each trapezoid are not the same, but oftentimes you will be working with problems where the heights are the same. So just make a note on that when you're working on a problem. If the heights are the same, then when you're setting up the area of the first trapezoid and then the second trapezoid and so on, you'll notice each one has a 1/2, so you can factor that to the very front. And then the change in x is the height. You could factor that to the front as well. So what you're left with is base 1 plus base 2, the next base 1 and base 2, and the next one. And what happens is this base, it's being shared by the first trapezoid and the second, so it's showing up twice. And then the next base also shows up twice. And so what happens is you can rewrite this as 1/2 change in x factored to the front. You have the first base right here. The second base has a 2 in front because it's used twice. The third base also has a 2 in front because it's also used twice. And that pattern keeps going until you get to the last trapezoid. This last base is only used once, so that's why it does not have a 2 in front. This example says use a trapezoidal sum to approximate the area under the curve of f, which equals 1 over x, from x equals 1 to x equals 2, and using n equals 5 trapezoids. So first we're going from 1 to 2, so what I want to do is look at the change in x. So our change in x is b minus a over n. So we end up getting for our change in x 1/5 or 0.2. So I drew the graph of 1 over x, and I only drew it from 1 to 2 on the number line. And I broke it up, so 1 to 1.2 to 1.4 to 1.6 to 1.8 to 2. So each interval is a width of 0.2. So I just colored in the first trapezoid. If you kind of think of turning it on its side, the height is the change in x. So the height is the distance between the two parallel bases. And again, this height of this trapezoid is 0.2. Again, it's kind of weird because we're calling it a height of a trapezoid, but it's actually the change in x on the number line. And then you have base 1 plus base 2. So base 1 is the height of the graph at x equals 1. Base 2 is the height of the graph at 1.2. So to set up our trapezoidal sum, what we're doing is we're taking the area of each trapezoid, and you have 1, 2, 3, 4, 5 trapezoids. And again, I just drew the first trapezoid, but you could draw the next one if you wanted in the next one. The area for each trapezoid has a 1/2 in it. So the formula for the area of the trapezoid, each one has a 1/2, so I'm going to factor the 1/2 to the front. Also, because each trapezoid has the same height, and again, that value is 0.2 or 1/5, I'm also going to factor out that height to the front. And then finally, to find, again, the area of the trapezoid, you do the 1/2 times the height, and then you do times base 1 plus base 2. So you can see for this first trapezoid, you have f of 1 plus f of 1.2. But then for the next trapezoid, you have f of 1.2 plus f of 1.4. And similarly, for the next one, it would be f of 1.4 plus f of 1.6. So what happens is we have f of 1 plus 2 times f of 1.2 plus 2 times f of 1.4, and then it continues 2 times f of 1.6 plus 2 times f of 1.8, and then finally for f of 2, it's just going to be f of 2. So I just want to emphasize that f of 1 and f of 2 are at the ends, so that's why it's just listed as f of 1 and f of 2. But all of these bases in here, this base is being shared by this first trapezoid and the second, so that's why we put 2 times f of 1.2 and 2 times f of 1.4 and so on. At this point, we're going to plug this entire thing into a calculator, and our approximation for the trapezoidal sum is going to be 0.696. This example says, given the positive function f on the interval from 2 to 18, selected values of f are given in this table. Let R be the region bounded by the graph of f, the x-axis, and the lines x equals 2 and x equals 18. Find a trapezoidal approximation for the area of R using 3 subintervals. So you can see from your table that your 3 subintervals are going to go from 2 to 10, 10 to 13, and 13 to 18. So what I want to emphasize is going from 2 to 10, that's an increase of 8. Going from 10 to 13, that's going to be an increase of 3. And going from 13 to 18, that's going to be a plus 5. So what's important to note is that our change in x is different for each one of these intervals. So that means when we're setting up our trapezoidal sum of 3 subintervals, we're going to set up each one individually. We can't factor out that change in x because the change in x varies. We can factor out a 1/2 because each trapezoid area has that value, so we factor that to the front. And again, besides the 1/2, the formula for a trapezoid is going to be your height or your change in x, and then it's going to be your 2 bases, so f of 2 and f of 10. And our next trapezoid, again, we have the 1/2, and then it's going to be our height or our change in x of 3, and then it's going to be f of 10 and f of 13. And then our last trapezoid is going to be, again, a height of 5 or change in x of 5, and then f of 13 plus f of 18. So next step, we're going to get all of these values from this table and plug them in. So f of 2 is 3, f of 10 is 6, again f of 10 is 6, and f of 13 is 6, and then finally f of 13 again is 6, and f of 18 is 7. So one more time, I just want to emphasize that since this change in x varies, we can't factor that value out in front, and we can't do the f of 2 plus 2 times f of 10 plus 2 times f of 13 plus f of 18 like we did in the previous problem. So instead we're setting up each individual trapezoid. So we get to here, and at this point I'm going to plug this straight into the calculator. So we end up getting 86.5. Alright guys, thanks again for watching.